Okay.
It's up to you.
Welcome everyone to this edition of the Physical Society Colloquium. Today we have a very special presentation on the history of the Department of Physics, given by our very own Professor Jean Barrette. Jean has been a professor in the department for quite a few years. So he was professor from around 1988 until 2011 and has been professor emeritus since 2011. Many of us know that he is a nuclear physicist, and that was his area of research for many years. He was, in fact, the director of the Foster Radiation Laboratory for about a decade. But today he's talking to us in his capacity as a physics historian. So he is also the curator of the Rutherford Museum, which you are all welcome to visit later on, presumably. If you ask Jean to give you a private viewing, I'm sure he would be very happy to do so.
Absolutely. But not today.
Yeah, and in addition, so he is also on the board of the Canadian Association of Physicists Division on the History of Physics and served as the chair of that board from 2013 to 2015. And so he should be very qualified to tell us about the history of physics in the department. So let's give him a warm welcome.
Thank you. I forgot to tell him that I changed my talk. In fact, in 2005, I did a talk on the history of the department. And I told him I can do the same thing. When I look at it, I didn't think it was very interesting. So I'm doing a talk now more on notes about the history of the department, which is like things that the students here, or postdoc, have to leave at some point. Is things you can tell people when you're away about McGill. Anecdote more than history. Okay? So, in fact, today, not today, but this year is the 140th anniversary of the department. It was really created in 1891. But before that, in fact, physics at McGill really started in 1854 when in the Department of Natural Philosophy and Mathematics, in fact. So in mathematics, philosophy, natural philosophy is physics. We all together, in fact, it was one course, one professor, basically. In 57, it states, basically, that the Faculty of Arts are now recognized possess the means of giving a sound mathematical and classical scientific education. Okay, there was one experimental course in the fourth year. That's all what there was at the time. 1864 is important. In fact, that's when the program in honors in mathematical and physics was created, in fact. And in fact, this is also when was created the Anna Molson Gold Medal, which is given to the best undergraduate students, in fact, in the enrollment. It was created in 1864, and I will come back to that. It will show up in a couple of examples I'll talk about. Okay, it was created by Mrs. John Molson of the Molson family, in fact, in honors of, for honors course in mathematics and physics. In fact, the department was really created in 1891. In 1889, it was decided to split this mathematics and physics department basically into physics, experimental physics, and mathematics as two separated departments. And in 1891, that's why it's on the 40th anniversary, the first chair of external physics was endowed by William McDonald. William McDonald was the owner of the tobacco company. The McDonald Tobacco Company, for people who like me remember the McDonald tobacco of the time. He was a very rich guy, in fact. He paid basically the salary of John Cox, in fact, was a fellow of Trinity College, in fact. And that's really when the department was really created, you can see. In 1894 was created the second professor, in fact, paid also by McDonald, who was a professor called Hugh Callendar, and I'll talk to him a little bit about, I don't have much time, so when I say I talk, it's one slide. He was also a fellow of Trinity College, in fact, specialist in thermodynamics, basically. Okay, so we are in 1891, and I give you, the talk is mainly about examples, in fact, more than about history, if you want. Yes?
Can I ask a question about that? Like, so the first two professors were endowed?
Paid by McDonald.
Okay.
At the time, it was important.
Okay.
Because industry was poor.
He was just interested in physics, or did he give a lot of money to other departments?
I'll show you in this slide. At the time, in fact, McDonald in 81 provided funds to build and equip, in fact, the physics building. This is the Sulis Library, if you remember. That is a photo, an old photo. In fact, this is really the Sulis Library. The front door was there. Now it's at the back. Now this door is condemned, in fact. It was paid by McDonald on top salary. He paid for the building. And was opened in 1893. In fact, This is the auditorium of that building, in fact, and if you go there, you can find, in fact, these steps here. They still exist in the bricks. You can see that. In fact, it was really a top-notch building of the time. It was built, in fact, at the time for $145,000, including equipment.
How long did it take?
3 years. 2 years. 91 it created and 93 was inaugurated. This building is full of interesting. For example, there was no nail in the building because this was important at the time for research. Nothing to do with Rutherford. And so the building was all made without iron into the building. Okay. So that's really important, and you visit the Solis, not now, it's closed now, but for innovation, you can recognize, in fact, some of the old physics department. I started to say, okay, I will use as a trade the chair of the department. So this is the history of the chair of the department, starting with John Cox, in fact, from 1889 to 1909, followed by Howard Barnes, 1909-1919, after 1935. You can see this very long time. Then after Shaw, then John Foster, and Gart Winton, and that's why I will stop. The reason I will stop here, because I have no time, and number two is that suddenly you get to the point where people are still alive, so you don't say a word about them because they can correct it. Okay? RLM is living in Vancouver, in fact. In fact, you continue. Sang Young is the 17th chair of the department, in fact. And in fact, this is the follow-up, and except for Tom and Mark, all the other people are alive and can meet them in the department, in fact. So that's why I won't say a word about them. So this Nick Detekasi, Tom and Mark, John Tom Olson, Das Gupta, me, Martin Grant, Charles Gale, Peter Goethe, and Sang Young. Okay? I just presented that because I had a photo. Okay. So John Cox, what can I say about John Cox? He was chair of the department for 20 years roughly. He did some very little research on X-ray, in fact. It's very important. In fact, in his Introductory Nature, it's written that keenly interested in all development of physics, he had not the practical training requisite for research in experimental physics. It was mainly about teaching. There was only two of the department. He was doing all the teaching, basically. And I'm still side, in fact. And this is the paint you see in the lounge, in fact. Say we're interested in X-ray, so it's kind of important to me. This photo is in our museum. If you go to visit the Macpherson Museum, you'll find this photo, in fact, is one of the first radiography taken in North America. Okay, it's the hand of a professor, in fact. It's called Photograph from the Life in the McDonald Physics Building, McDonald College, February 7, 1896. You have to, if you go to the Wikipedia, you can find out that X-rays were announced by Röntgen in November 5th, 1895, 3 months before that. So it's really the beginning, okay? And in fact, it looks terrible, but in fact it was not that bad. It was on the wall in the old physics building, in fact, and then when they moved the physics building to here, they store it. They store it in the basement of the Wong building. And in 2013, old people will know that, the young students have no idea, there was a major flooding, in fact. One pipe on Penfield, on the street, basically, not a small pipe, a pipe like that burst. And it flooded Montreal, in fact. The water went right down to Montreal Trust and these places. It really was serious. It also flooded the Wong building. And it flooded basically that painting that I didn't know we had. In fact, as Saverio, who suddenly one day showed up and said, "Are you interested in that?" It just came from this flooding area. Another thing which is very interesting is that in March 1896, Cox, in fact, published 2 papers. That's one of them. See, March is when the paper was published, which is like 5 months after X-ray were discovered. Published. It's better than publication of today. And in fact, the publication of the new photograph reporting the case of a bullet, which a bullet was photographed in the leg of somebody. So this is the person here. There's an X-ray tube here. On the other side, there's a photographic plate, basically. This is a power supply to drive basically the X-ray tube, in fact. And the idea was to find out the bullet in the leg. Somebody had been shot. The bullet stayed there, but it just healed. but at some point it started hurting. But they had no idea what the bullet was. So we took an X-ray picture to find out where was the bullet. This is a photo, in fact, from the article itself. It's terrible, the photo, but technically they're supposed to see where the bullet is. The painting was not that good at the time. Okay, so this is interesting thing that happened at McGill. In fact, you can tell that story one day. I said Hugh Callendar was also the second professor in the department. In fact, second chair of natural philosophy under McDonald. He was a specialist, in fact, in high precision measurement, in fact, of thermal quality using what's called a platinum resistant thermometer. If you take a very thin wire of platinum, in fact, the resistance will change with temperature. You have to realize, when I read the article, it's very interesting, they had no idea what the scale was. You just have a thin wire of platinum, the rest you have to worry about it. You have to normalize them, you have to calibrate them yourself. He returned to England, in fact, in 1898, in fact, and did some very nice work in England, in fact, especially about steam table. But with Barnes, in fact, and Barnes introduced, he measured, in fact, the heat capacity of water between 0 degrees and 100 degrees. See, this is a 1% effect here. So, in fact, you can see the dots here as dots, in fact, this is the curve. He could measure change in temperature of a 10,000th degree with this platinum thermometer. And this is the setup they use. They inject water at one end. They have a resistance in the middle that they could heat the water. And they have two platinum thermometers, one here, one there. You measure the change in temperature by using the platinum thermometer, knowing the power you put into this heating system, basically. It's a lot of fun to read, because today it will not show that way. You have to know exactly what is the resistance of the wire there. You have to know how much power you put in. You have to calibrate these platinum thermometer precisely. But more than that, you have to decide, this is calorie here. You have to decide what a calorie is. Today you buy some small box which has a scale in calorie and you trust it. No, he has, in fact, it's very interesting to read how you decide if it's 1 here, 1.1 there, or what's the precision of that scale. It's a lot of fun to read this paper. Okay. So I will suddenly slide on Rutherford, because normally I give a full hour talk on Rutherford. Everybody knows about Rutherford. Rutherford research covered all aspects of radioactivity. Rutherford was at McGill from 1898 to 1907, in which time, in fact, he wrote 69 papers on all his effects, these properties of radioactivity, basically, for which he won the Nobel Prize right after he left McGill. Left McGill in 1908, 1907, and 1908 he won the Nobel Prize in chemistry. And the most significant collaboration was between Rutherford and Frederick Soddy. Frederick Soddy, in fact, was just a demonstrator in chemistry department, probably the most famous chemist who came to McGill, but he had no permanent position, he was just a demonstrator, in fact. He was in charge of laboratory, in fact. The collaboration between Rutherford and Soddy, Soddy was here maybe 3 years, 2.5 years. But the collaboration was only for 18 months. And 18 months, from October 1901 to 1903, they wrote 9 papers. It's even today would be a reasonable rate. And there's only 2 authors, no more than 2. It's Rutherford and Soddy. And one of them is The Cause and Nature of Radioactivity, published in 2 parts, 1902, where, for example, he established the law of radioactivity. You all know this equation, dN dt equals minus lambda m. Okay, it's in the paper. In fact, I realized when I read the paper, this is exactly the equation I was using when I was teaching nuclear physics. It didn't change. F equal ma for that Newton invented, that's not true. Don't find that in Newton. It got all changed with, this didn't get changed. It's also, they demonstrated, in fact, that radioactivity is a change in atomic nature. It's really a change in the atom. And that was one result of this paper. And it took me a while to realize that the famous physicists at the time, J.J. Thomson, and all the ones that you know, didn't believe them. Today you read that, it looks trivial, you all know that. No. These people didn't believe Rutherford and Soddy. They had to convince the people that was true. Even if today looks trivial, it was not trivial at the time. People believe atoms are not unbreakable. And many people believe that for many years to come. Okay, next. Barnes. So Barnes was a successor of Cox. In fact, he was appointed lecturer in 1900, assistant professor in 1901. He was a student of Callendar, in fact. He was in 1907, and succeeded Rutherford as the McDonald physics professor, in fact, and became the second chair of the department. In fact, he resigned his post in 1919 because he was sick. He had a nervous breakdown and came back only many years later. One interesting data that he did, in fact, experiment he did, he measured the heat capacity, because that was the thing he did with Barnes, he thought it was interesting. He measured the heat capacity of supercooled water between 0 and -5 degrees. I've seen this, I have a photo, I forgot to put it there, of his setup. We have very few photos of setup, but I have one. It's physics, which is a mess. It's cable everywhere, it's a mess. How would you measure supercooled to -2 or 3 degrees? I'm sure this thing froze to him under time. You know, as soon as there's a dust, as soon as you touch it, it freezes right away. But he still managed to do it to -5 degrees. He worked with Rutherford. He measured the heat production and the radioactivity with Rutherford. In fact, later on, when he came back, he specialized in the study of physical properties of ice. In fact, he's the one who discovered the industrial form of ice called the fresel. Fresel is ice which is underwater, basically. And in fact, he wrote a book, and I have it here. He wrote that book on ice engineering, from which I pick up this photo. In fact, he discovered an explosive called termite. Termite is not a big explosive, it produces a lot of heat. So it was used, in fact, to break ice jam at the time. And it's an example of an explosion. Basically, you put the termite in the middle of a river, which is frozen, which is blocked, and you explode it, and basically it melts the things, and there's a chance, basically, that this is that you can break the ice jam. In fact, this is the people walking on the river in New England, in fact, carrying this explosive. And in fact, there's another photo which I find very interesting. This photo is people here in the middle of St. Lawrence River. The boat there, there's a boat there, it's a boat, is stuck in the St. Lawrence. And people are walking to the boat, basically, to install explosive or doing like that, basically. That was gorgeous. Okay? So that was the importance of Barnes. After that, he was succeeded by Arthur Eves. Arthur Eves is interesting also. In fact, Arthur is really not a physicist, he's a mathematician. He got trained in Pembroke College in Cambridge. He came to McGill in 1903 as a demonstrator and researcher in physics. But his area specialization was really mathematics. Then he worked with Rutherford, in fact, and they have a very good relation, him and Rutherford, in fact. He got involved in radioactivity, in fact, and he rose to rank associate professor in mathematics, then moved to lecture in physics, in radioactivity, so kind of physics, like he became McDonald professor in physics, in fact, and succeeded Barnes as chairman in 1919. One thing important to remember, he was the dean of Faculty of Graduate Studies up to 1935, from 1930 to 1935 when he retired. But I didn't write it down, but being the chair in 1919, he was chair till 1935 and dean of graduate studies till 1935. So for 5 years he was both chair of the department and dean of graduate studies. World was different, clearly world was different.
Jean,
yes.
How big was the department back then?
I erased these slides because I moved these slides out. They will have some data. It was in general something like 10 professors.
And how many students?
I wouldn't know. I can check all the slides I move at the end because I don't have time. I have that somewhere. I don't know if it's this year. It has, to be honest, between the war, it has fluctuates a lot.
Okay, yeah.
Go up and down and things like that. They bring a budget, depending on many things, in fact. Okay? Well, it's never big compared to today. It's no comparison. So he worked on nature of gamma rays, on things related to radiation mainly. He published many interesting textbooks, in fact. He published the first biography of Rutherford, in fact. This is this book here. It's a lot of fun to read. Because a lot of letters from Rutherford to his mother, between Rutherford and colleague and things like that, they're all there, in fact. I don't know where he got the information. Today it's all on the web or anything like that. He had to work on it. And it's really a very interesting book. In fact, one of his papers, I found it very interesting, the title is The Effect of Dust and Smoke on Ionization of Air. So basically, it's a smoke detector. You read the paper and you would have right, smoke detector, it's exactly that. See, you have basically, you flow here air, okay? You can put smoke into it, or dust. Okay, the air goes in and goes out, and it passes basically to a place where there will be some radiation source basically, and you will measure basically the level of radiation with a gold reflectoscope here. Well, not like today, but it's exactly a smoke detector. Exactly. He didn't patent it, he didn't make money with it, but to be honest, it's exactly that. It's impressive. Okay, I had a few slides on a few other people, not chairs. Gray is a very important person because you all know about the Compton effect. In fact, the first one who observed Compton effect was Gray. Gray, in fact, was an Australian physicist who moved to McGill in 1913. A lecturer. He did many publications, scattering of gamma rays and X-ray. Okay? And in 1913, he reported that scattered gamma rays are less penetrating than the primary rays. Basically, what you have primary rays. Okay? You scattered them. In fact, it's exactly the photo that exists in one of our photo lab. It's exactly the setup. You have a scattering. In fact, here you have a detector. Today, you put a gamma ray detector or whatever, measure the energy. At the time, they couldn't do it. But the way they did it, in fact, was measuring the thickness of the lead to absorb, basically, or to reduce the energy of the gamma ray. Basically, you have an ion chamber here. In front here, you put the lead detector, and you measure as function of angle, okay, how much lead you need to stop, basically, the gamma ray. And you find out that if you have a scattering at large angle, the absorption is bigger, which means the source, the gamma ray that hit the detector has smaller energy. This is really the Compton effect. Okay? Compton became famous partly because I forgot to explain basically the effect, okay? As a one scattering, as a mechanical, he didn't have that source, but the data are really from him, in fact. In 1924, he moved to Queen's University, where he became very important, in fact. And I had for a while a request to say Gray should be better known. He should replace Compton, in fact, for the Compton effect. Okay. Norman Shaw. Norman Shaw was the following chair of the department, in fact. He was a professor in physics at McGill College. McGill College at the time, and I'll come back to that, had the physics department in the agriculture faculty. And I'll come back to that later at the end. In fact, last person I talk about is a person in McGill College. For example, at the time they did a lot of applied research, in fact. He studied from 1919 the esteroids by projected method. In fact, he published a paper on small magnet and the effect of aging in Western cell. I tried to find the paper. I saw it, I read it before. Yesterday I could not find it. He had a paper, nobody had a paper like that. The title is something like The Stability of Western Cell were like batteries, over a 20-year period. I don't know how many of you can write a paper about 20 years. Okay? In fact, it's not quite. He wasn't addressing in 20 years. In fact, I would like in a museum to have these cells of the time, in fact. Western cells depend on the composition of the various components in a cell, basically. And you show, basically, that the cell is stable within 0.1% over 20 years, something like that. I thought it was gorgeous. When I saw that, I thought it was really gorgeous, in fact. He did, for example, things on ionization of gases. For example, this setup here is secondary cathode ray from gases. Basically, if you submit gases to cathode ray, can you generate more or different gamma rays, basically? This I like very much. He published many papers, in fact, some on thermodynamics. This setup, in fact, was built at McGill. There's a pipe, two pipes here, in fact, here. You have 12 meter high. So they had to move that setup in the arts building to find 12, where you can put the 12 meter or something. And the idea is you have two tubes here, okay? It could be two compound, or it could be compound, one is dry air, one is humid air. They will have different density. You try to measure the change in density, the change in weight for a given height. This, in fact, had the precision sensitivity of 10 minus 7 grams per cc. The way it works is that you bring the two columns basically to a setup like that, where you bring one of the column at one end, the other one at the other end. Here you have a mercury tube, basically a tube full of mercury, in fact, and basically if one side is heavier than the other side, the mercury will move. And you look at the end of the mercury tube with a microscope. That's how you measure, and you can change the angle, in fact. So you can change how much angle you need to move the thing back to the same distance than you had before. This is a very neat experiment, to be honest. So Shaw was responsible for these things. And other people, in fact, I promised to stop about these at 4 or 5 because I want to talk about women in physics. 4 or 5 I need. One other interesting professor is Vessel King, in fact, who was very applied. Did a lot of applied work, very nice work. For example, this was the frequency generator he was using at the time. Basically, you had a string here. You can adjust the length of the string. The string was at some weight. You adjust the length of the string, you change the frequency. So it was a frequency generator. And by measuring the length of the string, basically, you could tell what the frequency is. And with that, he used to measure, as function of frequency, the impedance, for example, of Bell bipolar 87 ohm receiver in a phone of the time. They had the headphone or the speaker. If you don't do anything, thing will resonate at one frequency. It could be very narrow. It's not good. You have to have in the phone that it's uniform over frequency. Otherwise, it resonates at the basic frequency. So that was the idea, in fact, is to say that what is the reactance, it changed by only a factor of 2. So it's not, you always have resonance, so it was working on that. Here, for example, it was working at submarine microphone receiver. So you have a microphone, basically, would change the capacitance here and measure the capacitance. So they were doing a lot of applied research at the time. They were not afraid about doing applied research. Keys, we're on the Keys auditorium here, that's why I'm using him. And David Keys, in fact, well, PhD from Harvard, was well known, in fact. So he came to McGill as a McGill research professor, in fact, and I like very much this paper. The first figure of the paper is an oscilloscope. You build your oscilloscope. You have electron gun. Here you have an X and Y electrode. Here you have a photographic plate. So when you're ready, you bring the photographic down and you take a picture of the trace. And what he was measuring, in fact, is basically the evolution of pressure in an explosion. So basically the idea is that you have a chamber with a spark plug. You put some gas here or whatever you like. You make a spark, it makes an explosion, and you put here piezoelectric cell with a metal sheet in between. So if the pressure change, it generates a voltage at the piezoelectric cell, basically, that got transferred to the metal plate, that got transferred out here and goes to one of the electrode here, and you will find basically, you see, you have a trace here, and when you have an explosion, in fact, you find a change you find a pulse. It's gorgeous to read that. What's the invention? What's it's not an invention, but what's the problem? The problem is to trigger the scope when the explosion happens. Okay? To this trivial, at the time was not trivial. It's the first time I've seen that where you build your scope for the experiment. Okay? That's different. Okay? It's very different. Next. Oh, fact, I'm doing quite well. I think I finish here. The last one is John. No, I have two slides. Foster. If you go outside, you see the Foster Radiation Lab. In fact, Foster obtained his PhD from Yale in 1924 and then moved to McGill as assistant professor. In 1926, he obtained a fellowship to spend some time in the Lisboa Institute in Copenhagen, talking to the people of the time about quantum physics. And in fact, he was mainly interested in Stark effect. Stark effect is how the line change under electric field. Okay? So in fact, I'll come back to that later. So stop here. But Ely Foster is best known at McGill for the construction of the McGill cyclotron, in fact, really a synchrocyclotron, that was commissioned in 1949, one of the first one. It started before the war, but the war stopped everything, so it did right after the war, in fact, and at the time it was the second largest cyclotron to exist in the world. So that's Foster in the middle of the cyclotron, basically. It could produce 100 MeV proton at the time. To build a cyclotron like that at McGill, I mean, you can read a lot of stories, how he got the principal, how he convinced company to give him money, and so it's a long story, in fact. That he could manage to build a cyclotron is outstanding at McGill. The last slide, in fact, about that, and I'm almost 4 or 5, is Got Wunton. Wunton, in fact, was graduating from Western Ontario. So he had a gold career in Western, but then in 1948 he came to McGill to become, in 1950, the founding director of the Eaton Electronic Research Laboratory. This building. In fact, this building is exactly what the Genome Building is now. At some point it was destroyed, they built the Genome Building, but this building was really the research center of Wunton, in fact. In his first year at McGill, Wunton worked principally on microwave optics, and took study of solids by microwave spectroscopy, electron parametric resonance, and so on and so forth. A detailed periodic measurements were made which led to our present understanding of magnetic insulating system, including measure and atomic clock. And in fact, Wunton can be considered the pioneer of condensed matter physics at McGill. In 1969, he quit McGill to go to Laval, in fact, as director of the research center in Laval, in fact. But really, for many years, for 13 years, he was the chair of the department and the leader of condensed matter physics at McGill. I say that for the condensed matter, you hear me, that's nobody. Okay, I'm 2 minutes late, not too bad, huh?
Perfect.
I want to switch completely. I said in my abstract, in fact, today we have EDI, okay, to all the discrimination and all the thing like that, basically. Okay, I didn't have that at the time. I give you a few very interesting examples. 3. So it's something very different. One is about a student of Rutherford called Harriet Brooks. That's her picture. In fact, it's a photo from Nutman of a graduation created from McGill in 1898 with first rank honors in honors again mathematics and in physics and in philosophy. And for that she was awarded the Anna Molson Gold Medal. She was the best student at the time. There were not many, but still. So she was first a student of Rutherford, the first student of Rutherford. Under his supervision, she completed an MSc. But in nuclear physics, with Rutherford thought nuclear physics is too risky. In fact, it was about electricity of some kind. And I have the thesis here, I forgot now what it is. Okay? After her MSc, she joined for a year the Cavendish Laboratory under J.J. Thomson. Second Nobel Prize. Okay? Then Rutherford called her back to McGill and obtained for a faculty lecturer position at the Royal Victoria College. If you go to down University Street, at the corner of Sherbrooke, there's a Royal Victoria College now, which is a modern residence. No, if you go down to Sherbrooke Street, the corner there, you can find a sign. This is where Royal Victoria College was. It was a residence of girls, basically, to which was associated 3 teaching positions. She had one of them. Because women cannot be professors at McGill. So they went to Royal Victoria College, in fact. It was not permanent, her position. She was entering in the permanent position. So in 1904, she took a more permanent position of lecturer at Barnard College. for Americans, I'm sure they know Barnard College. Barnard College is the women's college, was the women's college related to Columbia University. It's Ivy League women's college. You're talking serious university here. Today, there's no such a thing as women's college. In fact, men are allowed, but at the time it was separated. What I find interesting, in fact, and you can find that in her biography written by her relative, in fact, in this book here. It's full of things interesting to read. Should read that. I'll read you on the first. So she had to quit. She was told she had to quit because she got engaged to a professor in Columbia. Because professor could not be, in women's college, could not be married. Okay? And you should read that. She didn't want to quit. It turns out, a few years before, an exception was made for somebody, and people knew about it. Okay, so Brooks wrote to the dean of the, I'm quite sure that my duty will be, if anything, better perform under the new condition, but if new condition meaning married, but if I find that my new relationship at any time interfere with, in the slightest degree with the professional work, I shall of course at once tender my resignation, but feeling such an outcome, I should not be justified resigning. I'm sorry to have thus to appeal for your decision, but I cannot acquiesce without violating my deepest conviction of my rights. The dean replied to her, that's what I find interesting. You never see these letters normally. I know that they expect and wish that the woman should dignify her homemaking into a profession and not assume that she can carry on two full professions at the time. This is that most able men assume to be possible. Today we have this letter. It's in the book there. Okay? The world was very different. Okay? So she finally resigned. Her life is very interesting. She first traveled around the world with Maxim Gorky. How many of you know about Maxim Gorky? Not many, huh? Maxim Gorky was a playwright, was a writer in Russia, who had been thrown out of the country by Stalin, and so was living in Capri Island. To tell you how important that guy was, at some point they named Volgograd, the city Volgograd on the Volga, Gorgigrad. And this is not a village, this is a hell of a town. Okay? So it was important, except at some point he got in trouble with Stalin, he threw him out. So he went to live in Capri Island. It was normal for him, so she was not her boyfriend, her girlfriend, she was basically, it was a court. Maxim Gorky has a court. It was normal for him for lunch having 30 people, seems. Okay? What's important, in fact, is that, wait a minute. In 1987, she joined for a while. She had no salary, no position, something like that. So she was lonely. So in 1907, she joined for a while the laboratory of Marie Curie in Paris. Okay? Which means she is, in her short career, she worked with 3 Nobel Prizes, Rutherford twice, Thomson, and Marie Curie. I don't know how many of our students do that. And it's without email, without phone. It's impressive. The same year, 1907, she quit physics. She had applied for a job in England, but somehow it didn't turn out. And now she quit physics, in fact, to marry Frank Henry Pitcher in Montreal, the CEO of Montreal Water and Power Company. And in fact, her house, this is her house, is on the lot, in fact, of the Oratoire Saint-Joseph. The reason is that the 3 Brooks sisters are very interesting. So she married Pitcher, in fact, had a lot of money. Except the daughter, the sister of Barrette Brooks, I forgot her name, it's Brooks, but, and married, in fact, the owner of the land where the Oratoire Saint-Joseph was built. He gave the land to Montreal and say, you want to build the Oratoire? I'll give you the land. This person is called Blair Gordon, if I remember right. Sir Blair Gordon, he was a rich man. So that's why these 2 sisters were living basically, and in fact Blair Gordon had a bigger house than that. This house, is at the time I checked, was a retiring house for nurses, for sisters. The Blair Gordon house was a house for the singer, the Montreal boys choir, basically. And the third sister of Harriet Brooks, Mary Arthur-Eves, the chair I showed you before. Okay, so that's kind of interesting. In fact, the rest of her life at Montreal was not. One of her kids, and I forgot if it's a daughter or a boy, got abducted, in fact, at McGill at some point and disappeared in the mountain. So not everything is perfect, basically. Okay, next. So I say I will do three. So I did Brooks. Now I'll do Alice Viber Douglas. Alice Viber Douglas, she studied mathematics and physics at McGill. And because of the World War I, the study was delayed, so she went to London to work in the War Office as a statistician. And at age 23, she was awarded the Order of British Empire. She came back to McGill, in fact, and earned a bachelor degree and a master degree in 1921. Nothing wrong with that. Then she went to Cambridge, in fact, to work with Arthur Eddington. Arthur Eddington is the person that you all know about, is the one who checked the deviation of lights from a star, in fact. That's the famous Eddington. In fact, she wrote a paper with Eddington in the progression of stellar velocity with absolute magnitude. Okay. Then she came back to McGill, where she earned a PhD in astrophysics through McGill in 1925, and was the first person to receive it from Quebec University, and one of the first women to actually visit in North America. And it's very interesting. If you go to the history of the department on the web, you find out that the third person I will talk about, Laura Clark, was the first student in physics to earn a PhD in 1928. She earned a PhD in 1925. Because the supervisor was not in physics, he was in mathematics. But to be honest, she's the first physicist. It's kind of one of these things, you have trouble here to decide who is who. She was an astrophysicist, a member of the McGill Physics faculty from 1923 to 1939. That's 15 years, 16 years. Okay, she has many papers, very interesting paper, because they're all in different things. It's not working on one thing and do star A, star B, star. No. She had a paper, discussion of the winter and summer sky, such a absolute magnitude of star, the Stark effect in stellar atmosphere that she wrote with Foster, in fact. A report on 1932 total solar eclipse. She had non-astronomy paper, in fact, which I list here. Shows it's important. In fact, to show how important she is, this is a photo, and I have a series of photos every year. At the time, we had one per year, up to the war. So this is a photo from 26-27 of the staff of the McGill department, of the physics department, in fact, and you can see this list here. This is Barnes, Rayleigh, Shaw, that I talk about, Barnes I talk about, Eve I talk about, King I talk about, Keyes I talk about. So they're all the top notch of the department. She's always at the end of that row. And like, I have many 5 or 6 photos like that where she's at the end of the row. Which means they knew her value, clearly. And she had probably as good a value as most of these people in quality of her publication. Except she never got promoted. And I don't know why. And I was looking for a while to say, can I find a piece of paper who said there was a discussion in the chair meeting or whatever, discuss her. Because I'm sure that she would be interested. She was never promoted. And in fact, in 1939, she was appointed Dean of Women at Queen's University. And the Dean of Women, I don't know what it means. Okay. Among her work, in fact, she wrote a biography of Arthur Eddington, in fact. And she had another important title, Officer of Order of Canada, President of the Royal Astronomical Society of Canada. And in 1988, the year that she died, and one asteroid was named in her honors. So she was well known. But for some reason, she never got promoted at McGill. And I cannot find, I mean, I tell you that, it looks strange, but I can never find a piece of paper that said that. This is one of the papers I found it very interesting. Note ionization of cloud in expansion chambers. You have a chamber, you have a place where you can make a spark. Okay, and depending on the shape of the electrode and things like that, you have different. In fact, they are not photos, they are drawing that various shape of the explosion, basically. What I find interesting when you read that paper is that the spark was generated by Winner's machine. You all heard Winner's machine in your school or thing like that, to make, like a Van de Graaff, to make high voltage. That was used for research. The Winner's machine was a source of high voltage in their measurement, in fact. And the last one I want to talk about, well, I'm almost in time, it's impressive, is Laura Chalk. Laura Chalk, in fact, graduated in 1925 and won the Anna McPherson Gold Medal also, in the top notch. In fact, you want to know, Vicky Caspi was also a recipient of Anna McPherson Gold Medal. Okay, so a top-notch student, in fact. She then joined John Foster, who had just joined McGill at the same year, or the year before, for graduate studies, in fact. And this is from the 1925 McGill yearbook, in fact. Sure. In fact, it's very interesting to the yearbook, in fact. In fact, what's written here is Royal Victoria College, because the women were all part of this college, basically. At the time, that was the way it worked. This is, for example, John Foster came to McGill in 1924, assistant professor, so before the war, he was mainly interested in the Stark effect. His first paper in 24-26 discussed the Stark effect in hydrogen and helium, in fact. This is a photo one of his paper, Stark effect in hydrogen isotope. What I find interesting here is that this photo is part of it, one page, I think it's quite a page, it's 3/4 of a page, of a Nature paper. At the time, Nature paper was one page. So you have a page. You have a photo here, which is the photo. I read the paper, I don't understand anything. Because in 3/4 of a page, they talk about the line sigma, alpha, beta, and so on, and they all have slang. If you're not specialist in Stark effect, you have no way to understand what it's talking about. Okay? But he was really specialist of that. And Laura Clark was one of her first two students. I'll come back about the other one. Okay? Why is it important? So she attained an MSc in 26 and a PhD in 28. She's the first woman to have obtained a PhD in physics at McGill, forgetting about Douglas, like I was in mathematics. The title of her thesis was, the MSc was Potential Distribution in the Crookes dark space and relative intensity of Stark effect component in H, beta, and helium line at 492. Her PhD was more simple, was observed relative intensity of Stark component in hydrogen. In fact, why I introduced that, I would not have done that a month ago. But in fact, Peter Groter received an email a few weeks ago, was stating to see why they don't talk more about Laura Clark. Because, why you would talk about her? Because her results were the first published data to check the validity of the new Schrödinger wave mechanics calculation in Stark effect, in fact. Because this is it's all at the time, 1926. It's considered the first demonstration of quantum effects in spectroscopy. But somehow that got lost. Okay? And Groter is better at home for his cyclotron and things like that. But that's really serious. It's like it's my last slide, do you believe that? So after research assistantship with Foster, she won a Moses traveling scholarship to go to London to work with the Nobel Prize Richardson, which I don't know too much, except she, in her autobiography, she talked about him and was not very happy to work with him, to be honest. At some point she said, I have to work with him because he pays me, but she didn't like it very much. On her return, in fact, from England, she took a full-time teaching position at McDonald College. I told you McDonald College had the physics department at the time. She took one teaching position there. In the meantime, she married William Rose, who also had been a student of Foster. In fact, at the same time, Foster took the two students, her and Rose. Rose, she worked on basics, atom, hydrogen, helium. He worked on more complex line, basically. So this is why, to some extent, she's the one who demonstrated quantum effect, in fact. I put it in red here. Read that. After she had spent about 5 years in this position, McGill decreed that because of the state of economy, no wife could hold position in their husband's department. So she resigned. In fact, I took that from her biography. She lost her job and therefore was employed only intermittently as needed. I would have been pissed off. But she's a very nice lady. She had no grudge, in fact, because at her death she established a charcoal fellowship in physics. So two of our good students, in fact, share this fellowship. It's a $10,000 fellowship. In memory of her husband, William Rhodes, in fact, I was professor emeritus of agriculture physics at McDonald College. And I found it a bit strange because one day I was chair, this is when that fellowship was created, and they called me, the dean called me and said, yeah, we'll make a reception, something like that. But that was weird because it was a fellowship in physics, which is to one of our students. But to be honest, she worked in McDonald College, except McDonald College is not a physics department anymore. So the fellowship is to us, in fact. Okay, boy, I'm perfectly on time. As you can see, you may have more questions, but that's all what I wanted to say. Thank you.
Thank you. That was fascinating. So we have time for some questions. So I'm sure there are some. I have to run around to you with the microphone. You don't have to get too close to
I
it.
saw you waving that thing around.
Yeah, this is for the video. Otherwise, no one's going to hear you.
Oh,
So
okay.
you can't take it because I have to stay away from you. Otherwise,
Oh, I see. Okay.
Just talk.
Yeah, so I have a comment and a question. My comment is, can we bring back from the dead the facilities people who built the McDonald Physics building in 2 years? Because it's a very beautiful and functional building, and I think McGill could use those people. So I'm glad that's on the record.
I won't
now.
comment on that one.
And my question is, I noticed a lot of these people were hired in as lecturers and then got promoted to assistant and then associate prof. When did we switch to the modern system of coming in as assistant and then associate and then full?
I would not know.
Okay.
I'm not even sure I can find out, but I wouldn't know. It's one of these things, there's thousands of questions like that, which sometimes you learn, sometimes you don't, in
That
fact.
was like grade inflation. It's like we all come in like slightly more promoted than older people.
No, it's a lecture, in fact, be careful. McGill was built on the English system. And in England, still, the faculty lecturer exists.
Yeah.
Faculty lecturer is a perfectly valid permanent position. Okay? The same thing, for example, it's interesting, you all know about, what's his name? The one wrote the NM book, Jackson. Okay? Jackson, turns out, he was a theorist. So Jackson was in the mathematics department because when created physics, it was experimental physics. It's only in 1961, if I remember right, that theorists moved to the physics department. But when Jackson was here, he was part of, he had an office in the Foster Lab, in fact, but technically he was a member of the mathematics department. In fact, it's very interesting. I read the annual report one day. I said, do move and things like that. So I read, in fact, the annual reports of the physics department and the mathematics department, same year. In physics, they have a staff list, so Sitka and Andy show up. In mathematics, they don't say a word about it. They lose like a third of their staff, but never heard about it. Very strange.
okay. I'm sure there are other questions. Please raise your hand and I'll find you somehow. And I have to come to you with the microphone.
What's so clear, huh?
There's a question at the very back, of course.
Yeah.
Yeah. So it seems there were many people coming and going from or to Cambridge and McGill. Was there any special connection, or just is there any reason for that?
Yeah, yes and no. In fact, in a sense, Cambridge was especially in physics, was one of the center of research in the world and in England. First, there was a very strong link between McGill and England. In fact, I remember when I was younger, reading the calendar, today there's none, the calendar, so you see physics department, okay, all the prof. It was strange. The first time I read it, it was very strange, because half of the profs had graduated in England. Okay? It's the way it is. That's not true today, but I mean, I was alive, it's 50 years ago, but still. So that's part of that. There was a strong link between McGill and England. And when you go to England, Cambridge was one of, there's a few, I mean, Manchester was one of them where Rutherford went, but there's very few. Cambridge was the powerhouse, basically. Okay?
I have a quick question for the benefit of everyone here. So if people want a tour of the Rutherford Museum, they want to see the artifacts, what should they do?
Send me an email. If you go to the department webpage, there's a collection page where you click that. There's contact this curator physics McGill C at curator at physics. That's me. The letter will come to me. You can also send it to me directly. In fact, this morning, for some reason, I had a visitor from Ottawa, and I'm not allowed to do that. I'll let them in.
This is being recorded, Jean.
They were at the door, really. Because technically they have to register and so on, but they were at the door. And they were very nice people. And work at Atomic Energy of Canada. So but normally I'm not allowed, and I don't have a visitor yet, except I accept a visitor from McGill. And in fact, the students from Thomas Brunner said they would do that. They would send me an email. Because I prefer basically if you have a group of students who want to come visit. The reason you have to send me an email to organize it is because I'm here normally 2 or 3 days a week. It's more efficient to work at home. And like for all of us. And also I'm not sure what time I have. So we can organize it. In fact, a visit at the department, there's 2 visits possible. There's just the Rutherford Museum. Like I can take a talk, it's all equipment from, if you go to the web, you can find all of it, basically. So I tell you that, but if you go to the department web page, you go collection, you have a collection, you have a item about Rutherford collection, you have an item about McPherson collection. We can find all what you can see. And you also a place how to contact us. So if you come to visit, it takes minimum an hour if you want to visit both of them. I talk a lot, so very often, if I give you a tour, it's more like 2 hours. But because I talk a lot, in fact. But basically, because it's fun, you go to McPherson, I can explain many of the apparatus, in fact, which are a lot of fun. Okay, we have we have the photo of the first send of X-ray, but we have, for example, what's called a Maggie in Marconi time, in fact, was one of the first wireless receiver.
Probably best to keep your hand away from the microphone.
Sorry.
Okay.
And from 1905, in fact. And it's at the time, in fact, the tuner, or the selection frequency was invented by Marconi in 1908. Which means for a while, they could receive all the boats that would send signal get added up, which means there was not many boats. There was very few boats. And it's because at some point they got problem because there was too many of them that they invented the tuner to adjust the frequency. So we have tons of these. We have a very interesting Edison phonograph, in fact. Nothing with physics, but we have Newton's book, Optics, from 1704. That's the oldest thing we have. So if you're interested, in fact, you organize yourself. One is okay, but since you're there, you can have students, group, in fact, say you would like to visit. Like I said, it takes minimum an hour. If I talk a lot, it'd be more like 2 hours, an hour and a half. And yeah, it can be any time. Okay, it's better send me an appointment to arrange an appointment, because very often if I'm here, it's because I have something to do. Like today, I could not guide the people because I had to write a talk.
So unfortunately, we only have 1 hour for the colloquium. But if any of you have 1+ hours available, then I suggest you email Professor Barrette and ask for a nice tour. I went on it myself once with a bunch of high school students. It was really fascinating. So let's please thank Professor Barrette.
Thank you very much. It was fun.